Hello friends, welcome to my channel. Let's have a look at problem 449 again. Serialize and deserialize binary search tree. So in this video, as we promised, we're going to share a solution or different solutions using pre-order traversal based methods. So in this video, actually we're going to present two formats of pre-order traversal. And also we're going to present two formats of deserialization methods. So in total, 2 by 2, we have 4 different formats of solutions. So actually, each of the 4 formats of solutions can be tweaked and tuned. First, let's recall the problem requirement. So we are required to design an algorithm to serialize and deserialize a binary search tree. There's no restriction on how we serialization and deserialization algorithm should work. So we need to ensure that a binary search tree can be serialized to a string. So this is a requirement. And this string can be converted back to the original tree structure. So the encoded string should be as compact as possible. So here are 2 examples. So in my opinion, so the example 1 is still not very representative, right? So example 2 is a very special case, so we need to pay attention to this case. So in other words, at least we need to make sure our code or general method should work for this special case, or we do special treatment for this case. So the constraints for this problem are the following. First, the number of nodes in the tree is in the range given by the closed interval with the 2 ends and 0 and 10 to the power 4. So as demonstrated by example 2, so the whole tree can be null. Secondly, the node value is in between 0 and 10 to the power 4. And thirdly, the input tree is guaranteed to be a binary search tree. So this is the main statement for this problem. So next, let's look at the analysis. So here, the solutions in this video will be based on pre-order traversal. So actually, we can regard this video as a practice of pre-order traversals of binary tree. So this is the video 2 for this problem. So in this video, as we mentioned, we practice pre-order traversal of binary search tree in this problem context, or more generally for binary search tree. So recall that again. So in-order traversal of binary search tree yields increasing list. This is good, as we mentioned in the previous video. However, it's difficult, or if not impossible, to convert to the original binary search tree from the in-order traversal result, right? So this is the one point to be noticed. So, however, we can recover binary search tree from either post-order traversal or pre-order traversal. Both order traversals will be working. So here in this video, we're going to practice pre-order traversal. So in this not first, in the second video, so we will use pre-order traversal to do the serialization, in other words, from tree to string storage, and deserialization from string to the original binary search tree structure. As in the previous video, the idea actually is very straightforward. So assume that the pre-order traversal of a binary search tree is given here. So this tree actually is used as example also in the previous video, but the order, because we consider post order in that video, so the string is slightly different in order. So here, this is a pre-order traversal. Because this is a pre-order traversal, we know that the 5 actually is the root of the whole tree, right? Then by the binary search property, we know in the left subtree, all the numbers are smaller than the value of 5. In particular, we know 3 to 4 corresponds to the left subtree. In other words, we're going to use 3 to 4 to build left subtree. So similarly, we consider 10, 9, 7. These numbers correspond to right subtree. So overall, this task can be easily done by recursion. So here is our plan. So first, in order to do serialization, we need to do we choose to do pre-order traversal in this video. So we are going to give two formats of pre-order traversal solutions. And for the deserialization, we shall also give two formats of coding. One is in recursive format, and the other is in iterative format. So overall, if we consider the combinations, there are 4 different formats. So let's first look at the serialization, right? So here, actually, I can first write a depth first or pre-order traversal. So let's do this. So let's call it DFS. So root. So this is a hyperfunction which for clear. So let me first denote a results list. So this is empty. So you can think of this DFS function as a worker. So we are going to modify this result list because the result is mutable, right? So first, stop condition or base case. If not root, we just return, right? We do nothing. And otherwise, so we're going to append the root value, right? So if we like, we can do the conversion to string, right? Or we can do it after we get the number list. So let's do this here. First do the string. Then we can do DFS root left. Then DFS root right. So if you observe the order, first I append the value for the root, and then we convert in the string in the problem context, right? Then I do DFS for the left subtree and then right subtree. In other words, the order is root, left subtree, and right subtree. Therefore, this corresponds to pre-order traversal, right? So now, if we call this function DFS root, so we are going to get the number list corresponds to the binary search tree given by the represented by the root. So now we want to do the serialization. So here we can return the string. So we need to make it compact. We are going to join using a separator. So here we can use comma or we can use star or pound, anything as long as it's not numbers, right? So here is John result. So this separator actually is very important. So for example, if you consider a tree is 5 and then you have left child 1 and 2. So if we do not use separator, we get 5, 1, 2. Or if we consider one tree is like this, we have a left subtree that is 12. This also gives us 5, 1, 2. Just to let you know, this separator is important, right? So this is the one way of writing the pre-order traversal. So in the next version, so we're going to also provide a iterative format. So let's first content ourselves with this recursion format. So this is the serialization function. So now let's do the deserialization, right? So for this, first we get this data. So this data is a string, right? So we're going to first from this data we want to get this number list corresponds to the pre-order traversal. So this is actually easy. First, so we're going to do the array equals data split. So because here in the serialization we use the comma to separate. So here the splitter or the separator will be remain the comma, right? So this is for consistency, right? And then what we're going to do is that we transform this data to be integer x for x in array if x. So here I added a filter. So this filter is to deal with the case if the data is empty, right? So we cannot int on the empty thing, right? So that's why we see if x. So this actually keeps the the example 2 in mind. So next, we want to also write a worker to do the build process. So here, actually, we can write a helper function to build a binary search tree from this data. So notice that this data now is a list of integer, corresponds to the binary search tree in order traversal, right? So for this, I'm going to define a helper function like this. So this is the array, our original pre-order traversal for this, right? So what we are going to we can use data or array. It's the same. So ij, right? So we want to build a binary search tree starting from index I and ending at index j, both the two ends inclusive, right? So here, actually, first let's look at a stop condition or edge case, a base case. If I is greater than j, so we just return, right? So in other words, if I equals j, so this corresponds to a single node, right? So we're going to build a tree node. Let's see, we're going to let this value to be array I or array j, because I and j are the same, so we can return the node. So this is one case. Another case is that, so we can traverse this list, right? So from 5, so we traverse this up to some index which is larger than the 5. Then we stop there, and then we use this 3 to build the left subtree, and the remainder to build the right subtree. So this is very intuitive. So here, what we are going to do is like this. So we are going to write a for loop. So in range I plus 1. So in other words, we do not I corresponds to the root, right? And then what we are going to ending at j. So we write j plus 1. So what we are going to do is to check. We want to find the point array k, which is larger than array I. So this k corresponds to the index at 7 here in this example, right? So once we arrive at this step, so what we are going to do is that, so we are going to build a binary search tree using the array element, but starting from index I plus 1 and ending at k minus 1. This k corresponding to a number which is larger than the 5 in this example, right? Next, we're going to build the right subtree using the array elements, and then from k inclusive up to j, right? So the root node will be the tree node. So I'm going to value to be array I, and then we're going to connect the root left to be L, root right to be R, right? Then we return root, right? So this is one case. In the other case, if after we traverse this for loop, nothing returned, it means all the value in the list is besides I is smaller than I. In other words, all the elements in between I plus 1 up to j is smaller than array I, so they actually can be used to build the left subtree. So for this, what we're going to do is that, so we're going to have L equals helper array I plus 1, right? So up to j. Then we're going to have a root equals tree node. So the value will be the array I, and left will be the L, right? And then we just need to return the root. So notice here I directly connected the left, right, with L. So this actually forms a solution format for this solution, this problem. So now let's do a check. Wrong answer. So what's the problem? So sorry, we haven't called this function yet, so not finished yet. So here, so we have the data, right? And then we need to call this data, right? Call this function. So we are going to call return helper So this is the data. So we're going to call data and 0, and then length of data -1. So this is our we defined the worker and we want the worker to work, right? So that's it. So now let's do a check. Yeah, it passes the first example. Now let's look at the special case. Yeah, it passes the special case. Now let's look at the generic case. Yeah, it passes all the cases. So this is the one format of solution. So next, I'm going to copy this part. I would like to write another solution format. Let's change this one to be V1. So now let's look at here. So I'm going to delete this part and going to delete this part. So now we want to write another format of serialization. So this time I'm going to use iterative format of the pre-order traversal, and then for the deserialization function, I'm also going to use iterative format. So now let's first look at the serialization function. So for this, I'm going to define a pre-order traversal function. So define pre-order. So we can accept a tree node. So this actually is not very hard. So first, if not root. So I'm going to return empty list, right? So then let's initialize a result variable. So this result variable, we're going to return its final state. So here, because I'm going to use a stack, so I'm initialized as root. So this is valid because we have considered the case that the root is null. So if root is not null, we can initialize the stack as this. And then we're going to do the standard while loop, while s. So we get node equals s pop, right? So then we are going to append this node value to the result. Or you can do as in the first example, you can convert this root value to be a string here. Now let's use the, or we can do it after we get the list and then do it in one go. Let's take the latter to distinguish with the former, right? So now we want to check the left subtree and the right subtree. So notice that we are going to use pre-order. So the check of left subtree and the right subtree, the order is very important. So what the right order is that if node right. So we're going to stack as append node right. So we first check right, and then we check left, right. So this actually corresponds to the pre-order traversal. So afterwards, we return the result. So this is our hyperfunction. So next, so we're going to call our function, right? So the list is actually the pre-order traversal of the root, right? So you can write this as DFS, right? Because we are using stack. So if we use the graph terminology, graph theory terminology to interpret, this is indeed depth first search. So now we get the list. What we're going to do is to do the return. So here, let's write with some redundancy. I will introduce another variable, so called x. So I'm going to John, right? John the same. So we want to do string John. So actually, we want to transform each element in the list to be a string. So we can use map. So this map function apply a function, let's here string, to every element in an iterable. So here the iterable will be the list. And then we're going to return this x. So this x is a string. This is the serialization. So with that said, so we finished another format of pre-order traversal in iterative format. So this also gives us a serialization function in this problem context. Okay, now let's look at the deserialization function. First, I want to get the list out of this data. So this data is a string with a separator comma. So what we're going to do is like this: data split with comma, right? So this is inconsistent with our separator in the serialization function. So first, what I want to do is that, so we want to make a filter. So I want to change this to be integer. So in other words, int item for item in list if item. So here, this filter is important in this list comprehension. The reason is that we cannot apply integer function to an empty object. For example, if data is an empty string, so like in example 2, right? So this is to deal with that case. So now let's look at the generic case. So I'm going to make a head to be null, right? And then we initialize a stack to be empty at the very beginning. Then we scan the integer list called list, right? So then for y in this list, so first the overall structure is like this. So we are going to return the head after this for loop. So if this list is an empty list after this filtering, and then we didn't enter this for loop, so we are going to return null, right? This corresponds to the case in example 2. So now let's look at the general logic. For y in the list, so first, this y is already an integer due to the above treatment, right? So if not head, in other words, we haven't set the head yet, so we're going to make it a tree node. So tree node, the value will be y. And then, so we're going to put this this head into the stack, right? So otherwise, if the head is already set, then we first make a node out of this current value we are looking at. So then let's also write with this, and then we are going to check and compare the current value with the head value in the top value in the stack. So if y is less than stack -1 value, it means that y is in the left subtree, right? So we're going to do this: stack -1 left equals node. Otherwise, so this current value y is larger than the previous value. So for this, actually we need to do monotonic stack. So while stack and stack -1 value is less than this y, then we keep popping, right? Stack pop. So after we exit this while loop, the element u will be the value. So if we pop again, then we will have a value larger than the current y, or the stack is already empty, right? So in this case, we're going to set u right to be y. So this part, actually, you can try to make an understanding using this example here, right? So notice 4 is the left subtree, left child of 5, and 2 is the left child of 4, and 3 is the right child of 2, right? So the right corresponds to here, right? So no matter what's the case, so we're going to append this current node. So after this for loop, so we are going to return the head as we have already wrote. So actually for this problem, it's important to understand this monotonic stack. So notice that when we exit this while loop, so either stack is empty, so in this problem it's impossible, or the top element in the stack is less than y. In other words, so the u is the element which is still larger, is still less than y. However, so if we pop again, it will going to be larger, right? So because u is still less than y, so we're going to set this y to be the right of u, right? So this is the binary search property. So with that done, so actually we finished the second solution, right, for the deserialization function. So I guess it's better to have a check first. Yeah, it passes this special case. So now let's look at this example 1. So let's do the check. Integer object has no left. So here stack, we need to pop, we need to so integer, so tree node, so stack left equals node, stack pop, well stack, so here let's see, node, you're right, so here is not y, so we're going to put this node, right? So we have make this node. So now let's check again. Yeah, it passes all the cases. So I guess here up to now we shared 2 formats of solution classes for this problem. So we shared 2 formats of pre-order traversal. One is in recursion format, and the other is in iterative format. And correspondingly, we shared 2 deserialization function. One is in recursion format, and the other is in iterative format. So overall, actually, so we provide 4 different combinations of solutions to this problem. So I guess with that said, this is about it for the second video for this problem. So you're welcome to check the first video for this problem for the solutions using post-order traversal, and also you are welcome to check out the other practices of tree traversals in my playlist. So with that said, I guess that's about it for this video. Thank you.